So, as I promised in the morning, we will now look at multiple different ways of implementing Bayesian optimization. And I think the most instructive way is to just do it completely from scratch, without any library, without any external tools, because then you really see how actually simple it is to implement the equations that I described in the morning. So we will now start the second session with implementing Bayesian optimization from scratch. I think it's not even 100 lines of code. I will then relatively briefly show you how the same thing can be done using a library. And this is what I would also recommend you to do if you would actually use it. And then in the end, I will just also give a very short hint to this Excello program that we're currently running. So you have two options now for the implementation. You can just follow me and see what I'm doing, or you can try to program it yourself. I prepared a Google Colab notebook. So if you have a Google Colab account or some Google account, you can just log in and program it there, and then you don't need to set up any environment or anything. And who wants to actually program live? Some of you? Okay, then if you already can log into Google Colab, that would be helpful. I just wanted to, we can skip that. Just a quick reminder, we talked about the Gaussian processes in the morning. So the core thing that we need to implement are these two equations here in the bottom. And you will see in a minute how this can be done using relatively simple Python functionality. And I have this slide here in order to switch back and forth, so we can have a look at that again. But let me quickly show you. So if you want to program along, then go to this left QR code here. But how do you get it on your computer? I didn't think about that. Is there an email address I can send it to?
We can send it in the WhatsApp.
But you also don't have it on your computer, no?
Yeah.
Unless you log into WhatsApp online.
Yeah, most people have WhatsApp in the computer.
Okay, then no? There's WhatsApp web. You can just log in using your phone. Maybe that's the easiest way of getting it.
You can scan it on your phone and send yourself a message.
Yes. The link on the right, or the lower link, is the link to the fully filled solution. So if you want to program along, you should log into the left. If you just want to look at it and maybe run it, log into the right one. And then sorry? You're not using Colab? No. Okay. But what you can do is now make a copy of that document. Does anyone still need the QR code? Yes.
Oh, it's fine. We have them.
Sorry?
It's fine. We have them.
Yeah, see. Okay, no more phones. So what you can do here, if you're in there, you can save a copy in Drive, and then it makes your personal copy that you can edit and change.
Pascal, if we don't make a copy of that, whatever we write, it goes for everyone, right?
I think it's not editable. I think you can't change anything. So you have to make your own copy. You can try to put something in the first field, but I think it won't show up here. And I think it anyway doesn't have live synchronization, so. Okay, everyone has access.
Unfortunately, there's no cell phone connection for us, or at least for me, so I cannot. There's no way I can get to it.
I can make
type the link, then maybe.
So this should also work now. And I'm not sponsored by Enterprise. Works? Everyone logged in? Okay. So if you didn't do it yet, go on File, save a copy in Drive, and then it opens a new tab with your own copy. Yeah, you need to log into your Google account, but then it should work. That's tricky. Okay. Anyone still needs a second, or are you ready? Okay. So, as I said, we will now implement the entire thing that I showed this morning in less than probably half an hour, using just like very simple Python functionality. The only libraries that we use is NumPy and matplotlib for plotting. So the only thing we need here is NumPy and two libraries. Nothing else. You will see later Blowtorch and X, but for now we just need these two libraries. If you didn't use Colab before, you have to click Shift-Enter to run cells, or you click that small Start button on the left. So, apart from these two libraries, we need to define a function that we actually want to fit. And you remember the function that I was showing in the morning? Let me go back to... So the function that I was plotting this morning was this function here, and we tried to now do a similar thing. Does anyone have an idea how we can write that function as an equation in a very simple way? What could that function? Yes, exactly. It's a sum of two Gaussians. So what we do here is we define a ground truth function, our nature function, that we can then later ask about f given x. So what we do is define a function. We call it ground truth, and it receives a ground truth x, and it will, oh sorry, no, that's wrong. It gets an x, and it will output a f of x. So we write f, and now we have to write it as a sum of two Gaussians. And here I will just write exactly what I did in that tutorial. You can also change the parameters. So I had a Gaussian that had a factor of 1.6 times numpy dot exponent of minus 1.2 times the x minus 1.3 to the power of 2. And the second Gaussian plus 2.4 times numpy dot exponent of minus 0.9 times x minus 3.7 to the power of 2. So two Gaussians, each with a prefactor and a mean and a width. And you can also change that slightly. Don't go to crazy numbers, but you can vary your the numbers that are in this equation, and then we just return f. And then, of course, is everyone there? Yes?
I think you can scale the truth.
Oh, yeah. Didn't see it. Thanks. Okay, now we want to look at the function to see whether this actually is a good function to look at. And if we want to plot stuff, we always need some numerical representation of this function. So we say we split it in 200 x values. So we say we want to have 200 values of that function that we can actually plot. So we define the x values that we want to use to plot the function as linearly spaced values from 0 to 5, and then 200 of those. For that we use this numpy.linspace that will give us 200 equally spaced values between 0 and 5 here. And then this is just for purposes of actually dealing with that later. You don't need to worry about this. We need to change slightly the dimensionality of this for plotting, but it doesn't matter. And then we want to evaluate that function in these 200 points. So we say the ground truth of f. Oh. And then we just use our function here and apply it to these values of x. So we can also look into that. We can look what is ground truth of x, and then you see those are actually just numerical values from 0 to all the way to 5 in 200 small intervals. And we can do the same thing for f. And then we see we also get 200 values of our function. But this is an awkward way of looking at that, so we rather want to plot what it looks like. So we do plot.figure. If I'm too fast, please just interrupt me.
Yeah, can you go back?
Yes. Continue, yes? Okay. I'll keep that up here. So we want to plot what's going on before we do the initial measurement. So we do plot.figure, then we do plot.plot of the ground truth x and the ground truth y, f. And we want just a black line, so k minus. And we give it a label so it looks nice, and we call it ground truth. And then, because we're good scientists and we never plot anything without axis labels, we also say plot.x label, and we call that x. And we do a plot.y label and call it f. And we do the limits. And x goes from 0 to 5. And we do a y limit. And that you might need to adjust if you change the function from 0 to 3 here for me. And then we add a legend. And then we show the plot. And the golden rule is always don't plot the plot before you didn't do all of that, because later you're too excited and you will miss to add the axis labels. And then your supervisor will be mad at you for not showing any axis labels. Okay, so let's look at this. And here's the function that we also had in the presentation. So it's exactly the same plot.
Could you show it one more time?
Yes, sure.
One more time. Thank you.
And I really encourage you to change the parameters of your Gaussian distribution in the beginning. So they look slightly different, but make sure that they're not completely moving out of that plot or they're looking really weird. And ideally there should be also 2 optima, otherwise it's a bit too simple. Anyone still not there yet?
Not there yet.
Not there yet? Okay.
How did you choose the Gaussian parameter? Just for example? Or
It's just an example.
an example?
I just looked at it to see 2 maxima slightly different. Just a very quick interruption. If you open this link as well, then you will get the solution notebook. So if you're not quick enough, you can copy things over from the solutions to the main notebook. So you can open that just in a parallel tab. Okay, plot is working for everyone? Okay, now let's go back up one. We had one more ingredient. Apart from the ground truth function, we had some initial measurements. So what we do is we add some data to our initialization. So we say we have data values of x, and those were at 3 different positions. They were at 1.1, at 1.8, and at 2.9. And here, if you want, you can also choose different numbers between 0 and 5 that you want to use as the initial data for your training. And the y is just, again, the ground truth of these data points. So we picked 3 numbers for x. We then evaluated the ground truth. So that's running the first 3 experiments at these points. And now I also added them here to the plotting, so we can also see what they look like. And you don't need all of that. This is just to make it look nice, but you don't need to plot all of that. The important thing is just this part. So everyone has the data and also the plot?
Not yet the plot.
Not yet? Okay, we'll wait another. Also, if anyone has any questions about the commands I'm typing, also small things like what is NumPy array, all that stuff, let me know. There's no silly questions. Okay, everyone there? So if you run the plotting cell, you should see something that looks like that. So you have your own function if you changed it, and you should have 3 points on that function. And those are the initial data points for training. Okay, that's the preparation so far. So now we can start implementing first the Gaussian process model to fit this data, and then the loop that runs the Bayesian optimization algorithm that refits and refits again and again. And that's not much more work than what we already did. So if everyone agrees that we continue, I will go to the next part. So now we want to start with Bayesian optimization, and the core is the Gaussian process model. So let's define our Gaussian process model. And for that, we need I do it now in an object-oriented way, so I make a class that's called Gaussian process, and that class has a way to initialize it, a way to fit the Gaussian process model, and a way to predict using the fitted model a certain value. So I define, first of all, a kernel, and that's kernel function is the function that compares 2 different x values and evaluates what is the correlation between these 2 different x values. So we call them here a and b, 2 different values. You can also call them x1 and x2. And we first, you remember the kernel was this exponent of the minus of the distance squared. So we first calculate the distance squared. And you could in principle just say distance squared. Don't write what I do here. Is basically like a minus b to the power of 2. This works in principle, but if you want to evaluate that kernel on many, many points at the same time, this needs to be vectorized. It doesn't easily work like that. So we do that in a slightly more complicated way. We use one of these binomial formulas. So a minus b squared is a squared plus b squared minus a times b. And that's what we implement here. So we say we do numpy.sum of a squared in direction 1. So that's the dimensionality if we have many points at the same time. We need to reshape that again. And as I mentioned earlier, this is not necessary that you understand every single command here. Plus numpy.sum of b squared, also in that direction, and minus 2 times numpy.dot. That's the dot product of a and b, and we need the transposed of b in order to be here very strict about all the shapes of the different matrices that we have here. And then the kernel is just numpy.exponent of minus 0.5. That's just a parameter that I use here now, times the square distance.
That 0.5 is the smoothness that you are assuming.
Exactly, this is smoothness. If you want, you can also change that.
But why you put in 0.5?
That's smoothness is 1 because the definition of the kernel is distance divided by 2. That would correspond, I mean, in the textbook, this would correspond to the parameter 1. So this is just a fancy way of writing a minus b squared.
So what was the exact reason of not using the a minus b squared?
Because a will be later a array of many a's, and b will be an array of many b's, and you want to have like piecewise comparisons. So we want to compare every component of A to every other in B, and that's a vectorized version of writing that. But it's really just like, think about it, A is 1 point, B is 1 point, and you get the distance of A and B.
When you vectorize it, would it still be like a to the power of 2 dot or comma 1, or would it be like some I and it would be some like force cycle to go through every single
if you have a, like if you want to write this as a for loop,
Yeah, yeah, maybe I know.
I mean, you can try to rewrite this somehow as a for loop and going through all the components.
Sorry, no, I mean, like, so if we have like this vector, if A comprised of vectors, would it still work like just like this, or would?
Yes, that's the meaning. Like it works for lots of different A vectors. So A is actually here can be a matrix.
So what is the point of the comma one in that?
That it sums only in the first dimension. That's to like you square it first, and that's component wise, and then you square in one direction, and that's doing like x1 squared plus x2 squared plus x3 squared for one point. And then for the next point, it does the same thing, so it sums in all directions for all the different A points. Don't worry about it too much. It's just assume you have like many points of A and many points of B, and you want to have the distances of all of them.
Why do we say A but not B?
Because A and B have different. They're like one is a column vector, the other one is a non-column vector. That's why you also have A and B T here. Okay, so we have our kernel. That should work. And now we have to implement these two equations here in our Gaussian process model. So we define a class that we call Gaussian process. It has a init function. And we initialize it with a certain kernel, so we give it a kernel function, and then we just save that kernel as the kernel that we.
Return key.
Sorry?
The kernel function should be return key.
Yeah, that's a good point. Otherwise, the function will not do so much. So, and now our Gaussian process model needs, as I said, a train and a predict function, as most machine learning models do. So we define two more functions. One is the train function, and the train function, what does the typical train function get? Data. So what is the data? Yeah, x and y values. So we give it x and, I mean, we call it yf here. So we give it x and f values. So we save them again as internal variables. So when we train the Gaussian process model, we give it data points x and the observations f. We save them internally in the model, so they're not lost. And then we evaluate the kernel matrix that looks at all the differences or covariances between the data points x and themselves. So I'll quickly go up here. I'll go back to the code in a second. So what we do here is we calculate this part of the matrix here, so the data itself with the data itself. That gets the 3x3 matrix in the upper left corner. That's something we can always pre-compute because that's part of the training data. And we look at how are the distances between all the training data points and the other training data points. So what is the distance between x1 and x2, x1 and x3, x2, x3, and so on? And what kernel entries does this correspond to? So this is the matrix K that we define here. That's the kernel of X and X itself.
I'm sorry, maybe that's too basic, but what does the self function do in this case?
A self is just looking at what is already stored in that class. So you store things, I mean, you initialize the class using a kernel, and then you save this as a object internal function in this case, or object internal thing. And then you can call it later using the self.kernel when you do the predict. Or you can use later self.x if you want to get back the training data. And then, as I said earlier, the only thing that we really do, and that's costly in the Gaussian process, is we need the inverse of this matrix here. So if you look at these two equations, there's this k matrix to the -1. So we need the inverse of that matrix. And this is the costly part of the computation of the Gaussian process model. Because if you have 1,000 data points, then you are computing a kernel that has size 1,000 times 1,000 of kernel entries, and you need to invert that matrix. And that scales with the dimensionality of, or the number of data points to the power of 3. So if you have 1,000 data points, that's like 1,000 times as expensive as having 100 data points. And that's 1,000 times as expensive as having 10 data points. So it scales very quickly with the number of data points. So that's what we want to, for example, not do every time we run these equations. That's why we pre-compute it during training. So we say self.k inverse is, and now we use NumPy. So NumPy gives us a way of inverting matrices in a numerical way. So we can do the inversion. And here we can write self.k. So we compute the matrix k, and then we do the inverse of that matrix. And because that's not fully numerically stable, we add a very, very small entry on the diagonal. I mean, you can do it without probably, but it might run into problems. So we add very, very small numbers, 10 to the -6, on the diagonal. Four closing brackets here. So numpy.I makes a diagonal matrix, and it puts a 10 to the -6 on all of these diagonal entries and adds that to the kernel. That makes it a bit more stable to make sure that you can always invert it. And as I said, you can try without that part here. It might work depending on how you chose your initial training data, or it might just fail. So this is all that needs to be done during training. So we calculate a kernel matrix between all the training data points, and then we invert it, because all the other things that are in these two equations, they depend on the data points that we want to do predictions on. So we can only do all the rest during prediction time. We cannot do that in a pre-computed way during training. And for the prediction, of course, we only get x values. So if we want to use the model and predict, we only pass it the x values, but there's no f values yet, because that's what we want to get. And now if we look at, is everyone there? Yeah. So now we look at the things that are missing here. So we do get, we have the k to the -1. We already have the observations f, that's what was saved here as self.f. But we need k star and k star star in order to calculate that. We go back to this matrix, so k star is basically this part here. That's the covariance between the training data points and the new prediction data points. And we need k star star, that's the kernel matrix between the new prediction data points and themselves. So we need to calculate these two things. And here we can just basically copy this line here. So we have a k star, ks, and that's the kernel between x and x pred. And then we can copy it another time and call it k star star, and that's xpred and xpred itself. And because we vectorized this kernel earlier, we don't really care whether those are matrices or vectors or scalars. It works for everything. And that's why we had to calculate it in this slightly more complex way. And we also don't care if this is just one data point that we want to do predictions on or a million data points, because that kernel matrix can handle all of these different dimensionalities. Okay, so now we have k star and k star star. And now all we have to do is basically implement these two equations. And that's not too complicated. So we say, oh, wait a second, I did a mistake. We don't need to save that. This is not necessary. We can just do it locally and then delete it from, it gets deleted automatically. So we do the mean prediction. And that is, now the mean is k star transposed times that inverted kernel matrix times f. So we say here that is ks transposed. Then we do a dot product. And we put here the inverse of k, so we say self dot k inf. And here we need a self now because that's not defined in this function. So we need to look it up in our storage. That's why we saved it here as a object variable. So we write here self dot k inverse. And then we do another dot product with self dot f. So that's just like basically this equation here in code. Yes?
In that case, we also don't need to save xpred because we're not going to reuse it after.
Xpred we don't need, I mean, yeah, that's only used inside the prediction function and then not used anymore. Whoa, that's a good point. Yes. And then we say the covariance is k star star. That's this part. Minus ks dot t. That's the star transposed again. Dot product with self dot k inverse. And another dot product with k star. So we have both of these equations now evaluated during prediction time. I was not completely honest about like what is the difference between covariance matrix and the standard deviation. So we need to actually, like, the standard deviation is the square root of the covariance matrix. So we need to calculate we need to do one more thing about the dimensionality. So let's call this covariance S, and then we do covariance is covariance S dot ravel. That changes the dimensionality again. We don't need to worry about this. And then we can get the uncertainty. Is just the square root of the diagonal of the covariance matrix. No, wait a second. I need to check actually my code because there might be a problem in my code, but let's do it like that for now.
What does the Ravel function do?
It changes we added like a dimension earlier here to some parts, and it gets rid of that extra dimension again. That helps you do the vectorization. Because in the end you want a vector back. So for every prediction data point you want to have one mean and one variance prediction. I need to check this in the example code. I think I used the wrong one, but we need to check. So this is the whole Gaussian process model. I would not recommend you to use that for production, but in principle this does everything that the normal Gaussian process model in any other library is doing. And if you compare this to implementing a neural network from scratch, this would be more like a few hundred lines of code just for the neural network model. And Gaussian processes are really that simple to implement. Everyone there? Okay, let's test it. So we just plotted our initial data. So we initialize our model, GP model is an instance of our class, and we initialize it with the kernel function that we defined earlier. Oh, GP. And then we train it using our training data, that was data X. And again, we need to reshape it for vectorization purposes. So this is the training part, and then we can do predictions. There seems to be a problem.
You have I, not F, like in the data.
Session question. Where, sorry?
Second line, in this last one. Shouldn't that be
Yes, that should be F. Oh yeah, okay, that was the problem. So now I have to rerun the thing. Oh, did I call it data F or did I call it data Y? Oh, okay, let's do it properly. But it still crashed, no? Sorry? It might be that thing, so let's do here actually that thing. I need to check that again. Yes. Yes, this seems to work. So, yeah, return use directly that covariance S in the uncertainty. So all we did is we initialized our model using that class. We gave it the kernel function to initialize it because the init function needs the kernel. Then we trained it on the few X and F data points that we had, these 3 data points. And then we predicted it for the 200 X values, the whole X range. So now we can, in principle, plot our Gaussian process model as a function of F. And that's what we do now. So we go back up and copy that code for the plot. And we add one more line where we plot actually the mean and the standard deviation of the Gaussian process. So we do plot in order to get the blue line, the mean, and the blue line has evaluated now at 200 data points. So we can use here the ground truth x, ground truth x. I also have Revel here, but I need to check whether that works. And then we do model.mean. So we plot the mean over all the x values.
You solved the previous problem. I mean, I still have the.
You use the covariance S here on the dike. So we're plotting now the Gaussian process output. So we want to plot the mean over all the x values. And just to make that look nice again, I am adding a label here and call that GP mean. I add the color to make it blue. And then I want to also plot the uncertainty bound. So I want to color this, and this can be done using plot.fill between. And we fill it between, we use GTX as the x values, and then we use model mean minus model uncertainty as the lower bound, and then we use model mean plus model uncertainty for the upper bound. And we make it a bit transparent. And also make that blue. Oh, no. That works? No? Oh. What is the problem here? But what is, did I make a mistake that I don't see right now?
I think it's that button that
The model mean was not one-dimensional.
I did it with flatten and it worked.
So if I use flatten here, it works,
For me it did.
but it doesn't do the fill between still.
Why?
For me, it says that the model mean is not one-dimensional either.
We can do model mean Revel,
But
should work.
So you
the problem is it's not
Oh, in
It's in your code.
yeah, I also flattened that.
Mu is not, it should be mu.
No, everything was flattened.
Mu is not
let me see, maybe it... Oh yes, I forgot a line here. Yes. I skipped that line. Oh, and that also, okay, that was the problem. This was nonsense here. So the mean, yeah, we did revel on the mean, but not on the other thing. Now that fixes it, yes. So now we have revel here, but not here. Yes, okay, thanks. So for those who want to follow, we had here the revel on the wrong thing. So you have to go back to your Gaussian process model and do revel on the mean, but not on the covariance.
Does it make the mean like one dimension?
Yes, yes, yes.
Okay.
So for every x, you get one mean. Yes. And for every x, you get one mean and one uncertainty value. And we put in 200 x's, and we get 200 means and 200 uncertainties. And we can plot them here, and they look smooth. So now we want to do that again and again later. So we make that here into a function. Oh, that was a mistake. So we define a function that is called plot. And it gets the ground truth of x, it gets the ground truth of f, it gets the data of x, it gets the data of f, and it gets the, let me see, the model mean and the model uncertainty. And then we can reuse that function to plot again and again later. So we don't want to copy the code many times. And if you want to try it directly, you can run it here directly, and then it doesn't change the output, so you still immediately see it. Everyone there? Not yet? Which one do you need to look at?
The final one.
Yeah. Okay. To not lose too much time, I will continue now. So we have that plot function. It works. Well, we can skip that. That was already done. I mean, yeah, this line of code should be here. So we can plot it and it works. Or not. Yes. And now we need to switch over to the Bayesian optimization. So we need two small functions to do that. We need one acquisition function. So given a mean and a standard deviation of a model, we now need to decide what is the informativeness. So we just implement a very simple function here. We call it the acquisition. And this is the upper confidence bound. And it gets a mean and an uncertainty, and it just returns mean plus uncertainty. This is the most simple acquisition function we can use. We can make that more complex if we want to, but this is just the upper line of this blue interval here. And then we need to, given that acquisition function, pick a new data point. So we make a function that's called select experiment, and this is getting all possible experiments, so all 200 possible values that we can in principle run, and the values of the acquisition function in all of these 200 values. And now we want to just pick the maximum. So all we do here is we say x next. And now we want to pick the maximum of the acquisition function, but not actually the value, but the maximum position. And that is done with numbyte.argmax of the acquisition function, and then we pick, that is giving us an index. So it tells us the, 57th data point in the 200 has the maximum. So we then use exactly that one at this index. So that's the next best experiment to do. Yeah, I will put the square brackets in a second. So we look at all the acquisition function values, 200 of them. We find out what is the maximum index, and then we index our 200 x values using that index in order to get the x value that has the maximum value. And we also want to return what is the actual acquisition function value. Everyone there? So we're now approaching the last cell, because the last cell is actually the entire Bayesian optimization loop in just a few lines, because we have now all the ingredients that we need. We have the Gaussian process model, we have data, we have an experiment wrapper, which is the ground truth function, we have the acquisition function, and we have a selection function. So everything is there. So now we need just a small iteration loop with a couple of lines of code. So we define how many steps we want to run. Num steps is equal to, 6, 7. And then we have an iteration. So for I in range num steps. So this is an iterative algorithm. So we iterate 6 times. And in every iteration we do the same things. We already have a trained Gaussian process model from outside. So we can directly use the acquisition function. So we can evaluate the acquisition function as written down here. And we use from our initialized model, we use the model mean and the model uncertainty. So we use the previous the initialized Gaussian process model directly. And then we run, using that acquisition function, we select the parameters. So we get x next by selecting the experiment given that acquisition function here. And then this is the big thing here. Now we run our experiment. So given the next x data point, we get a f next. So this is where you basically now do all the magic. So now you have to control your experiment or train your machine learning model or do whatever to get the actual next observation. Here, of course, we do a shortcut. We just use that function that we defined. But in reality, this is where you run your experiment. And get a new observation, f next. And then we can use our plotting function to plot everything. And then we have to add the data points that we got. The new data point we have to add to our data set. So we say data X, and we append a new data point to our initial data. So we have 3 data points in data X, and then we append the new data point there. We do the same thing with our data F, and that is appended with F next. So we append a new X value to our previous data points and the new F values to our previous observations. And then we make a new Gaussian process model and fit it again and make new predictions. So I just copied the training of the Gaussian process model in there. So we make a new Gaussian process model, we overwrite the old one. We train it with the new data points, data X and data F, and now they contain 4 points. Initially we had 3. We added 1 now in the first loop, now they contain 4. So we fit the model with 4 data points and then overwrite the model prediction, mean and uncertainty. And this is hopefully working. So I run this now, and now it makes all the plots. So now we have our initial model with 3 data points, then the model with 4 data points, the model with 5 data points, and so on. So it fits everything, it iterates, finds the next data points, and finally finds the maximum. Yes, sure. Does it work for most of you? Yes? If you look at the tutorial solution, I will now speed up a bit because there's 10 minutes before lunch, so I would like to cover a bit more. If you look at the solution, what I did is also plot the acquisition function to really have everything from my presentation. So in that solution here, if we just quickly run it, you will also always have a plot of the acquisition function in between. So you also see what's going on in the acquisition function exactly if you want to look at that. And then you can really produce everything that I showed in my presentation this morning. So now we have 10 minutes left, and I would actually like to ask you, there's 2 options. I can show you how, and this is much quicker, how this is implemented in X and ProTorch, which I would recommend as the go-to libraries right now for Bayesian optimization. Or I can go back to my presentation and present a bit about how this can be extended to real-world experiments. So who would like to see the X ProTorch part? And who would like to see the application aspects? I think that's a bit more. I mean, everything like the tutorial is here linked in my presentation, so you can go through it. It's also not much more code. It just uses the ProTorch and X library in order to fit the same problem and then a more complex problem. So I would say I go back to my presentation and do the rest of that. So I hope you saw now that this is not magic. It's really relatively simple integration of the math that I've shown in the morning. And it can be done almost without any additional tools apart from NumPy. But as I said, I would not recommend you to use that for production. It's really just for learning and understanding it. If you want to use anything, go to this Expo torch, or also just a small teaser, contact me. We're right now running, we implemented this in a very convenient software that can talk to your experiments. This is meant mostly for industry users, but we're running an academic test program right now. So you would get support in implementing this, support in designing your experiment. If you want that, contact us, and you also find all the links and email addresses in my presentation. But I will now finish with the more complex workflows in the next couple of minutes. So there's a couple of examples where we apply this using experimental partners in many different scenarios. This ranges from additive manufacturing, where you have different slurries that you want to optimize in conditions. You can make polymer synthesis. You can do lots of different stuff. And always what you need to do is having a kind of idea of how you make this loop. Like, what are your parameters? What is your parameter space? And what are your objectives? But there's a couple of examples where this is not so easy. Your workflow is really complicated to do your experiment. And this is some of the things that we're trying to develop. And there's one example, and it's photovoltaics materials, that I would like to quickly motivate this with. This is done in the lab of Christoph Brabeck. He's also in Erlangen. And he has a solar cell manufacturing line, basically. He developed it over more than a decade, where he can fully automatically make solar cells out of many different materials, layers, and measure in the end the solar cell device performance. So you get in the end, in like tens, maybe even like more of experimental steps, one single number out, just the efficiency of a solar cell. And very recently he added also the synthesis of materials to that. So he doesn't even start with the materials, but he makes new molecules and then uses these molecules in different layers of solar cells to get in the end one number out. So literally like 100 or more experimental steps to get one single number in the end. And the space of experiments is huge. You have like a lot of parameters in the synthesis, a lot of parameters in the device, in the processing, and so on. And casting this to one single loop, where you in every loop do the whole workflow, is kind of very wasteful. So we're running really costly experiments to just get one single number. And we are kind of ignoring everything in between. We're ignoring the characterization data of the molecules. We're ignoring characterization data of the single thin films. We're ignoring all the things all the way in the end to the device performance. And then we try to learn how do all the parameters that we changed influence this device performance. And this is really not a clever way of doing experiments. What we as humans would do, we would look at all these in-between measurements, try to figure out how do they influence, how do they correlate with the device performance, and then select experiments and stop experiments in between. We wouldn't make 100 molecules and put all these 100 molecules into 100 solar cells, but we would subselect the molecules based on their properties, and then maybe only make 10 thin films, and from these 10 thin films, make 5 solar cells to get the best one in the end. And this is very non-trivial to put such a complex workflow into patient optimization. Just a few more details. What we did here is we had libraries of A and B compounds, and we could react these A and B compounds to small molecules that basically consisted of A-B combinations. From just having 1,000 A and B fragments, you can already make 1 million molecules. So in principle, we have a search space of 1 million molecules here that we can synthesize in the lab and then put into solar cells to measure which one is the best one. What we can do in principle is we can like initialize with some subselected data set and then like narrow down the search space. What we actually did is like we automated synthesis and device characterization, but then we also computed some molecular features in order to inform the Gaussian process model about what is actually the characteristics of a molecule, using simple DFT calculation to get HOMO-LUMO levels, sizes of molecules, and so on. So we have already some knowledge about the molecules. And then we did patient optimization, basically. So we had 100 initial experiments, trained the model on that, and then iterated in batches to get new synthesized molecules, new solar cells and get the device performance out. So we did it the hard way. We did everything automatically and then get the efficiency in the end. And we could show that basically using some initial molecules, we can optimize the efficiency up to 21% fully automatically. And then if you optimize a bit more manually in the end, you can really boost the efficiency even more and get very high device performance out of that experiment. But I would never do it like that again. I would extend the Bayesian optimization approach. And if you have more complex workflows, I would also recommend you to think a bit beyond the simple Bayesian optimization. So as I already said, we can use the experiment as a black box and just acknowledge that there's like maybe 100 steps here in between, and then we get one single number out. But this is like really, really costly. And we're wasting a lot of intermediate measurements without really learning all the complex correlations between our molecules or whatever we want to optimize, all these intermediate measurements and the final measurement, because we are wasting or kind of ignoring all the in-between data. What has been done very often is this funnel type approach as an alternative. So we start from, I don't know, 1 million molecules. Then we run DFT calculations on all of them and say, okay, we only select molecules that have a HOMO level of 4.2 electron volt and above because we have certain criteria. And then we can run, I don't know, synthesis experiments or something more complex maybe, to have another criteria and then like narrow down further and further using predefined criteria to tell us what is a promising molecule. But this requires a lot of prior knowledge. We already need to know how does the HOMO level here correlate with the efficiency in the very end. And very often we don't have that intuition. We don't know what is a good molecule property in order to get a good device performance in the end. So very often this funnel type of approach is much more clever in terms of efficiency because you don't need to run all these 1 million molecules in all the stages because we narrow down, but at the same time it might be biased. We might miss molecules that are promising just because they're not obeying these rules that we set here. So we filter them out and we're missing maybe interesting stuff. And I think one of the most promising ways of approaching this problem is a mixture of both. So we need to learn on the fly to basically think about how far do we want to advance every molecule or every single experiment on this funnel and reconsider all these different criteria on the fly. So we learn on the fly how does the final efficiency of a solar cell, for example, depend on these intermediate measurements. So we can adjust on the fly what is our measurement criterion and what is the next best thing to do. Would it be the best next thing to do to put another DFT calculation on one of these molecules to see what is its HOMO level in order to see can we make more molecules here? Or is the best next thing to do to take another molecule from this batch here and actually measure the device performance to learn more about the correlation between the device performance and some intermediate measurement? There's always one most informative next thing to do, but it doesn't always necessarily need to go through the whole funnel and include making the molecule, making the thin films, making the solar cell, getting the efficiency, but it might be more effective to just do one step at once, basically one of these orange points, one level further, have one more observation, and learn on the fly how do we deal with all of those. And there has been ways, this is in the literature very often called gray box optimization. So we're not treating the experiment anymore as a black box, but more as a, let's say, not fully opaque box that has multiple steps. And the simplest way of doing that is saying the experiment has two steps. It has one step that measures some proxy property. This could be, for example, you have a molecule, you measure the DFT calculation, the HOMO level, and the second experiment would be you actually make the molecule and measure the HOMO level. So two steps. The DFT HOMO level might be a proxy, not always perfectly accurate, but a good trend with the actual measured HOMO level. And if we want to optimize HOMO levels for some application, we could treat this as a two-step experiment. And there has been initial work, mostly by the group of Frays here, in the last couple of years, dates back, it's not too old, that tries to do or extend Bayesian optimization to this multi-step scenario. We also started working on this to make this more applicable to experiments. So we basically have now a acquisition function that decides whether to run step number 1 or step number 2 in every iteration. We can make certain assumptions and say, like, I don't know, a DFT calculation has cost 1 and an experiment has cost 10 because it's more complex. And so we are not measuring the number of iterations we do anymore, but the total cost. And on the y-axis here, you see the distance to the global optimum. Let's assume we have a pool of 1,000 molecules. We know in this like fake scenario, we know the HOMO levels of all these molecules, so we know the outcome of all the experiments, and we also know the DFT HOMO levels of all these. So we can now fake an experiment and always select, do I want to now do a DFT calculation of one of the molecules, or do I want to do an experiment on one of these molecules, and see how far am I away from the global optimum, finding the best HOMO level among all the molecules as a function of the cost. And you can see here the random exploration again, very slow. I mean, it's getting better over time, but it's very slow. You see here the Bayesian optimization that always runs the full chain. So it does all the experiments and just looks at the experimental outcome in the end. And you can see the gray box optimization, where you take into account intermediate outcomes and then learn on the fly. How does the molecule and the HOMO level measured in DFT are correlated? How does the DFT HOMO level correlate with the experimental HOMO level? And then you can exploit this and you can decide, given my data, does it make more sense to run an additional experiment to learn better that second mapping? Or does it make more sense to run another DFT calculation to learn better the first mapping here? And the first mapping, as you can imagine, is much more complex because it maps from a molecule to a HOMO level. That's a very complex function. The second function maps from a HOMO DFT to a HOMO experiment. That's hopefully a very simple function, just some correction. So that first function is maybe more complex than the second function. So you might want to get more data for the first function, but we leave it up to the Bayesian optimization to decide how often do we want to do the first and how often do we want to do the second function. And here we assume that the first function is more complex than the second function. That's what we typically have in experiments. We have a good proxy experiment that tells us a lot, but not everything about what we actually want to do. And then we have another more complex experiment that measures then the really accurate values. But this also works for other scenarios. So this would be, the 52 would be like complex first experiment, simple second, but the cost is inverted. But it also works if the first experiment is very crude. It doesn't tell us much about the actual outcome. And the second experiment is more costly and more complex. So the gray box optimization works in more or less all scenarios. So even if you try to optimize solar cell device performance and you measure HOMO levels as your proxy experiment, and there's no linear relation between the HOMO level and the device performance, so that second function is also quite complex. You can learn on the fly the correlation between those and then make very clever decisions of what to do next. And this, of course, opens a lot of opportunities to explore more complex workflows. You don't have to do a two-step workflow. You can have many different with branches. You can do DFT calculation or more costly calculation. You can do multiple experiments. You can learn in between thin film characteristics and learn what to do next. There's one approach of like mixing Bayesian optimization with more complex experimental workflows to not be forced to basically cast your complex experiment to this simple loop, but you can define your experiment as you want and then adjust the algorithm to whatever workflow you have. And I think with that, I will end my presentation. I hope you had fun. I hope you learned something about Bayesian optimization today. I hope you can also apply that to your research. If you have more questions, you can ask now or later. And I thank you a lot for your attention. One more tiny advertisement. We are organizing a summer school in September in Karlsruhe. This will be AI or machine learning for materials. We already have a quite nice lineup of speakers. So if you're now hungry for more summer schools, check it out. We will also focus on very similar topics. So property prediction, inverse design. We have one day on large language models, a lot on automation, self-driving labs. So might be interesting also for all of you or your colleagues. So please check it out.
Deadline for registration?
Sorry, it's open. You can apply.
When is the deadline for registration?
There is an early bird deadline, and that's in. You see it on the website. I don't know, somewhere in May. June 4. Okay.
Is there any other question? Okay, let's end this speaker.